Okay, so let's continue taking a look at Newton's laws of motion. Now, I do want to point out, if you're one of the people who skipped the last part of the last one, it's not actually something that you'll need to know for things like the AP test or anything like that, but I find it very interesting. I would recommend checking it out because I talk a little bit about the understanding of science before what we now consider to be modern science. And it was actually far more complex and reasoned than most people would think. It also underscores why Newton's laws of motion are so important. They actually explained everything, but only if you pay close attention to them. And they did so if you analyze things mathematically. If you're only talking in terms of, oh, it looks like it's doing this, you can make an argument for both sides, but it is only in the introduction of the mathematics that Isaac Newton's work stands head and shoulders above all of the other work until his time. And that brings us to Newton's second law of motion. Now, Newton's second law is very much unlike a lot of other things. I can't really do a direct comparison to Aristotelian physics, not that I would here at the beginning. But the reason why is it's that part that I mentioned in the primer video on this. Let's jump back up there. What Newton brought to science, which was a deeply mathematical, rigorous analysis. You collect not only observations, which are a form of data, but you collect numerical data that you can do mathematical analysis on. Isaac Newton, in many ways, opened the door to us to understand that the universe, for whatever reason, follows mathematical rules. And with mathematics, we can actually predict what the universe will do pretty much precisely, or at least mostly precisely, depending on how good our measurements are. It set up an idea that's called deterministic, a deterministic universe. One where if you had enough information, the rules are almost clockwork where you can predict what will happen. Now, your mileage may vary, but for the most part, on the grand scheme of things, there are a lot of mechanisms that seem to happen in the universe, and we can mathematically model it. And in doing so, that's what brings us all these natural, or not natural, but these modern wonders that we have. Something from projectors, to lights, to indoor plumbing, to even buildings that reliably don't get knocked down, particularly in wind and rain and so forth. Take that as you will. But the important part of that is what we get from specifically Newton's second law. Newton's first law basically tells us, okay, if everything's going on script, stuff just keeps doing what it's doing, unless you push it around. And so Newton's second law steps in and says, okay, now we're going to tell you what happens when things go off script. This is not something that was easily done beforehand. You can only vaguely describe, well, things will do this, at least for a little while, and then they will stop. With Newton's second law and the other things that he set up, we found we could make predictions of how long something would do, how long it would take for something to stop going up and for it to come back down, and so forth. In fact, on the other two laws, I will give you the textbook definition for it. On Newton's second law, I don't even know the textbook definition of it, and I wouldn't bother with it, honestly. What we really need, Newton's second law is one of the most important because it is the equation. One of the most fundamental and important equations in physics. If you know one equation and how to work with it, make it this equation. This is possibly the most important equation in all of physics, because without understanding this, you can't really get an understanding of anything beyond that, or at least I would argue that. Now, this is the modern way that we take a look at it. What Newton actually said was something a little bit more complex. I'm going to write it up here on the board, but if you're not dealing with calculus-based physics, then please promptly forget this. Isaac Newton said the following. Most of what Isaac Newton actually dealt with was with a concept that we now understand to be momentum. As I mentioned in the previous video, when he uses the word motion, he's actually more accurately referring to momentum, which is kept track of with a lowercase p. Now, in the Principia, he introduced a decent amount of calculus, and so this was one of the things that he actually worked with. And this is another form of it where it says the sum of forces is equal to our time derivative of the momentum. Now, I did want to bring that up. You can do chain rule on this, where the momentum is your mass times your velocity. And if your mass does not change as a function of time, in other words, your mass is constant, it will simplify down to F equals ma, which is what most people are familiar with. When's a position, or When is a circumstance where the mass would not be constant? Well, a good example of that would be airplanes, rocket ships, and a host of other things. Things that noticeably change their weight. Turns out you burn a lot of fuel, and fuel can be kind of heavy. So when I was doing aerospace engineering classes, it was common for us to have to go to the more complex version of it because we had to account for the fact that we were losing mass over time as the plane flew because it was burning fuel. All right. That being said, that plug out of the way, the vast majority of people are needing this equation. F equals ma is how it's usually listed. A couple things on this. Most people will write it like this. Do yourself a favor and do not accept ever writing it like that. Not even when you're in a hurry. I wouldn't recommend it at all. There are two main things that people overlook when they're trying to work with this, and this exemplifies that. The two main things that they overlook that they very much need are this, the sum of, and these, the vector signs. Now, force is a vector, acceleration is a vector, mass is a scalar. So the net force, the sum of forces, will be equal or will point in the same direction as the acceleration of the object. Forces cause accelerations. That's what we take away from Newton's second law. And that is how we explain why things move. I apologize, the bells are still going. That's how we explain why things move. Things move because we push them. I've got a book here, and it is at rest. It will tend to stay at rest unless I apply a force to it. Now, we end up with some acceleration. There are other forces acting on it. There's a force of friction. There's also a force of gravity. There is a physical contact force from the table. But of the things that I want to point out is the acceleration is exemplifying that, actually. This equation, the acceleration comes not from one force. Many people say F equals ma. They're given a force. Let's say I push this book with 10 pounds of force, and I have a non-zero acceleration. It speeds up. But if I push here, I'm pushing with 10 pounds, or 5 pounds, whatever I said just a moment ago. I'm pushing with the same force, and I have no acceleration. How is it I can apply a force and yet have no acceleration? Well, the answer is it's not just one force. Do not do F equals ma. Always keep in your mind that it is the sum of forces, or this is often written as F net. The net force equals our mass times our acceleration. Now, I can't not include the vector signs. If you're in a hurry, you don't necessarily need to write them, but never, never, never forget those vector signs either. Now, the common mistake people make is if I apply a force to something, it will accelerate based on its mass. That's not true. I'm applying a force and there's no acceleration because my force is working with or against all the other forces acting on this object. And objects will have an acceleration, will change their motion based on all of the forces acting on them. You must look at all of them, which is why when we work with forces, we draw something called a free body diagram. We'll introduce that later on, but the free body diagram is supposed to be so you can see all of the forces so that you can add them together properly. Now, the other thing you got to keep in mind on this that a lot of people overlook is the vector nature of both forces and accelerations. Which way that force is directed is fundamentally important. It will also determine how it interacts with other forces because we are adding things up. That's what this means. It's a mathematical operator, which means add things up. It's a summation, the sum of forces, where summation is the fancy term for add stuff up. We have to add them as vectors, and we've learned that in class, how we work with vectors. We split them into x's and y's, we add the components together, and then we find our resultant. All of that comes into play with Newton's second law. The most common mistakes that people make, I know I'm repeating myself, but I cannot stress this enough, because it's what people make the mistake of, and it ends up throwing them completely off. Never look at one force unless it is the only force acting on your object. You must look at all the forces acting on the object and add them as vectors, and that will tell you what will happen to the object, how it will accelerate. I can push here and we get a different outcome than me pushing here, partly because of my direction and partly because of the other forces acting on it, and that will vary depending on your circumstance. But this simple-looking equation can explain all the motion that you see in the universe, for the most part, if you know how to apply it, but applying it is the complex part. Never forget, all of the forces need to be included, and their directions are important. I'll go ahead and write this out. Sum of F is sum of all forces acting on the object. And only on the object. If you have forces from the object acting on something else, you don't include those, only the forces acting on the object. We'll talk more about that in the next one, Newton's third law. M is the mass of the object. And acceleration, A, is the acceleration of the object. Now you can take a look at some of my other videos. I show you actually solving some of these, setting up a free body diagram, keeping track of the forces, adding them all up properly as vectors, and using that to make predictions about the acceleration. Or, if we have information about the acceleration, we can work the opposite way, and we can find information about the force, or maybe the mass. That's the beauty of these equations. They show us relationships between this idea of the forces, the mass of an object, and its acceleration. So as long as we've got enough information, we can find any of the others. All right, let me see if I've got anything else in my notes on this one. This one's kind of an important one to keep track of, and it's one of the most functional ones that you will use throughout physics. In fact, I, and oftentimes the AP exam, will refer to it simply as Newton's second law. You want to keep in mind that the second law is the equation one. That's one of the key ones that you want to work with. One final thing, and hopefully this video is going to be outdated sometime in the near future. On the AP exam, at least currently, they do not have the sum of forces equals the mass times the acceleration. Last I checked, they've got it where they've divided both sides by the mass, and they've got the acceleration is equal to the sum of forces divided by the mass. These two statements are the same thing, they just look a little different. They might have F net instead of sum of forces, but I think last time I checked they had sum of forces. They've stuck with this form of it for a while. That is not the common form that I'm used to. I don't know why they're doing it, but I've got a few ideas. I'm not in charge there, so just be aware that this is what it looks like as of the filming of this video on the AP equation sheet. This is how you will see it in my class or in any of my videos, because that is the way that I always learn it. All right. This is Newton's second law, one of the most functionally important, and there are plenty of videos that show me applying it so that you can see it at work.